Good afternoon, everyone. Hello, and welcome. Hope you're all having a good weekend and a good start to the reading week. I'm just going to do a little bit of test review for the Math 1 at A3 first midterm. Yeah, we'll just get some problems done from the problem sampler just because our first test will happen right when we get back from the reading week. So, yeah. If you have any questions, feel free to send me an email. And without further ado, let's get started. So, our first question asks, can we find the 999th derivative of f of x is equal to sine of 2x? Now, for your own sake during the test, I hope you don't actually compute 999 derivatives. Well, let's see if we can come up with techniques that will help us evaluate these a little more quickly. So let's see if we can find a pattern. So let's start, we're going to denote the nth derivative. So this is notation for higher order derivatives. F to the superscript n, where n is in brackets, is the nth derivative of f. So in this case here, we would have f0 of x is going to be equal to just sine of 2x. Now we know that if we have sine functions and cosine functions, we know the derivatives of sine functions. So if we take let's say we move around the circle, as we move around this clock, we're going to be taking derivatives. So we cycle between these four: sine, cosine, negative sine, and negative cosine. So if we were to do the same thing here, we would have the first derivative of x be equal to cosine of 2x, but we also have to multiply by our chain rule here, so we'll have 2 to the power of 1. If we were to take the second derivative, we would have that the second derivative is 2 to the power of 2 times the negative sine of 2x. Let's just give ourselves some more space here. And I'm going to write also that this is 2 to the 0. We're going to have the third derivative of f be equal to, we'll have the same thing. We'll have now negative 2 to the 3 cosine of 2x. So another 2 is popping out from the chain rule. And then we'll notice that the fourth derivative of x is going to be, now our negative cosine is going to turn into a sine again. And we'll pop out another chain rule again. So here, the thing that's changing on each term, first off, we have an extra 2. So our power is increasing by 1 every time. And also, each of our sines and our cosines are following the circle. So our sines, cosines. So if we were to make a guess for that 999th derivative, we could say, okay, the 999th derivative is going to be equal to, well, it looks like we'll have 2 to the power of 999 because our factor of 2 is being influenced by that nth derivative there. Also, we should think about, okay, if we're going around 999 times, we're going to want to know where we're ending in our circle here. So if this is number 0, this is 1, 2, and 3, we can also think about, as we progress through, the remainder of our division by 4 will be the one that we want to stop at. So this is almost, we can think of it like modulus if you've done any programming. So if we were to look at 999 mod 4, well, that's just going to be equal to 3, because we know since 996 divided by 4 is equal to 0, so adding 3 will make our remainder be 3. So if we're ending on number 3, we're going to want to end on a negative cosine of x. So we'll make this negative cosine of x. And that should be our final answer. Oh, sorry, cosine of 2x. And that should be our final answer for this one. So this one's going to be D. All right, so not too bad. Let's keep pressing on. so let's say we wanted to do the same thing. Let's find the 68th derivative of x to the power of 421. Let's see if we can find a pattern again. So if, let's say, f of x is equal to x to the 421 here, then I guess we could write, okay, the 0th derivative of f is x to the 421. If we take the first derivative, that's going to turn into 421x to the 420. If we take the second derivative, notice all we're going to be doing is continuing to power rule. It's going to be 421 times 420 times x to the 419. Or in particular, for the nth term, if we have the nth derivative, we're going to have 421 multiplied by 420 multiplied by ... up until we get to the 421st minus n. 421st minus n plus 1. So, for example here, if n is 2, then we would want to have, so for example, let's just check to make sure our formula works. So if we have f, the second derivative, we would have 421 multiplied by, our final term here would be 421 minus 2 plus 1, which is 420, which fits with this. So that works out. Now, we also need to, we also need to multiply by our x power, so we'll have x to the power of 421 minus n. And that also should work out. So as we take n derivatives, n times we're going to be multiplying downwards, and we're going to be subtracting from that exponent. If you've seen like data management in high school, you can also write this using factorials, but since we haven't really talked about that in the course yet, we're not going to worry about it. So this is going to be our formula for this derivative for the nth derivative. So if we put this over here, if we want the 68th one, the 68th derivative of f of x is going to be 421 times 420 times all the way down to 421 minus 68 plus 1 to the power of x to the 421 minus 68. So if we were to simplify that, that's going to be the same thing as 421 multiplied all the way down to 354 times x to the power of 353. So that's going to be our final answer for that one. All right, so let's keep going. We'll press on. So this question asks, let's find the domain of f of x is equal to the ln of x minus 5. Well, remember that the domain of a log function has to take in a number greater than 0. So we'll have ln of x implies that x has to be greater than 0, the input. So in this example here, we'll notice we have two lns. We have two possible places that restrictions can arise. So for the yellow ln, we know that we have to have the ln of x minus 5 greater than 0. And then from this blue ln right here, we know that we have to have x minus 5 greater than 0. So we need both of those restrictions to take place. We need both of these to be satisfied. So solving for this one here, we can, if we want the ln of x minus 5 to be bigger than 0, that's the same thing as saying we want x minus 5 to be bigger than e to the 0, which is 1. So x is bigger than 6. For this blue condition here, we just have x is bigger than 5. And, well, since this restriction is more restrictive, the fact that we need x to be bigger than 6, it wins. So the domain of f is going to be equal to just the set of all numbers, x, in the reals, such that x is bigger than 6. That's not too bad. Now, this next question tells us to find the derivative of f, and it's the same function as f. We should just remember, actually, since being able to take a derivative. So if a function is differentiable, we know from class differentiability implies that it's continuous. And if it's continuous at a point, that means it's defined. So since our function is not defined for x less than or equal to 6, we also cannot take the derivative when x is less than or equal to 6. So that's just a nice little thing to remember, just in case we were ever trying to look at the domain of where the derivative is also defined. But let's say we were going to take the derivative. So f prime of x, that's going to be equal to, now we know the derivative of ln x is 1 over x. So we're going to have 1 over the inside, 1 over the ln of x minus 5, times the chain rule, we need to take the derivative of the ln of x minus 5. Now that derivative is also going to be, so we'll have 1 over ln of x minus 5. That derivative is going to be 1 over x minus 5. And then the derivative, we need another chain rule derivative of x, but the derivative of x is just 1. So that's going to be our final answer. So that one's not too bad. So let's keep pressing on. We're going to simplify the expression cosine of the arcsine of x. So let's do this using our right-angle trigonometry here. So if we're taking the inverse sine, remember sine normally takes an angle and spits back a number for the ratio of the sides. So if we have an arcsine, that's going to take a number representing the ratio between the sides and spit back an angle. So if we were to draw a right-angled triangle here, if we're taking the arcsine of x, that's going to give us an angle theta here. And in particular, the arcsine of x, that's the same thing as the arcsine of x over 1 being equal to theta. And since we know that sine of theta is equal to the opposite over the hypotenuse, let's draw our right-angled triangle like this. So our opposite side is going to be equal to x, and our hypotenuse is going to be equal to 1. Now, if we were to take the Pythagorean theorem, we'll solve for our final side is going to be the root of 1 minus x squared. So now we're able to use our cosine formula. So remember, our cosine of theta is equal to the adjacent over the hypotenuse. So in this case, it's just going to be equal to the root of 1 minus x squared. And since we substituted theta in here, we actually wanted to find the cosine of theta. So this is the exact value we were looking for. So this one's going to be A. All right, not too bad. So, yeah, let's keep pressing on. Okay, so we're going to let f of x be given by 6 over pi x plus the sine of x minus pi over 2. And the question actually asks us to find the inverse, the derivative of the inverse evaluated at 3. Now, let's remember back to our inverse function rule. So the inverse derivative, if you want to calculate it using a nice little formula, we can take the that the inverse function, or the derivative of the inverse, excuse me, is 1 over f prime of f inverse of x. So if our goal is to find the derivative of the inverse at x is equal to 3, well, what we can do is we can find f inverse of 3, and then we can plug that into f prime. Now, this is really nice and handy because, do you remember at the very beginning of the semester when we often had to take inverses of a function where they might not have an elementary inverse? So this is one nice place where it comes in handy. So first, let me just plug this into our formula. So if we're looking at f inverse prime of 3, that's going to be equal to 1 over f prime of f inverse of 3. So now in an aside, we'll find f inverse of 3. If we set that equal to x, that's the same thing as saying f of x is equal to 3. So if we want 6 over pi x plus sine of x minus pi over 2 equal to 3, well, what can we try that makes both expressions nice? Well, we notice we are dividing by pi here, so we'd really like to choose x to be a multiple of pi to cancel that out. And we also want to cancel this out. We don't like the sign. The sign is a transcendental function, and we need to make sure that the output is going to be a nice integer, 3. So what I'm thinking is, okay, what if we were to try x being equal to pi over 2? That way, if x is pi over 2, well, this sine function will be equal to 0. And this first term, it'll cancel with the pi, and also it'll reduce the magnitude of that 6. So if we try x equal to pi over 2, that'll give us 6 over pi times pi over 2 plus sine of pi over 2 minus pi over 2. Well, that'll be equal to 3 plus 0. That's equal to 3. So actually, that's exactly what we were looking for. So we can plug that into this expression right here, and we'll get that this is equal to 1 over f prime of pi over 2. So there's just a couple things left to do. We just have to find f prime and then plug in pi over 2. So let's calculate f prime over here. F prime of x is going to be equal to, by our power rule, 6 over pi. Plus, we'll take the derivative, so we'll have the cosine of x minus pi over 2. And if we were to take a chain rule, that would just be the derivative of x, which is 1. So if we were to plug in, we have f prime of pi over 2. That's going to be 6 over pi plus the cosine of pi over 2 minus pi over 2. Cosine of 0 is 1, so we have 6 over pi plus 1. So if we were to plug that into this expression here, our final answer would be 1 over 6 over pi plus 1. And that should be good enough for us to leave. We can just leave it in this form. So that's going to be our final answer. So that one's a nice little application of our inverse function rule there. All right, good stuff. So we'll keep pressing on. So question 15 says, okay, the following limit represents the derivative of some function f at some number a. We should state such an f and such an a. Now, what we should do is, we have an all of the above answer. So what we can do is let's try checking a couple functions. We'll try a, we'll try checking another, and if we find that 2 of them work, then we can stop. Then we can just pick all of the above. So let's start with a. So let's say we're taking f of x here. Now, the derivative of a function at a, so f prime at a, f prime at 0, that's going to be the limit as x, as h goes to 0, of f of 0 plus h minus f of 0 over h. So in this case, if we were to plug that in, that would be the limit as h goes to 0 of, we have the ln of 1 plus h minus f of 0, that's just going to be the ln of 1, which is equal to 0. So we can actually get rid of that. All divided by h. Okay, so this one looks like it works. We've already matched the limit that we were looking for originally, so a is going to be correct. So that's really nice and handy. Let's see if we can match that with b as well. So f prime of 1, that's going to be the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. So if we were to sub in those values here, f of 1 plus h, that's just going to be equal to the ln of 1 plus h. F of 1 is ln of 1, which is 0. Aha! So this one also seems to match. So since we've concluded that A and B match, then it must be that all of the above match. Now, if we were to think about why this works, notice that we're just F here versus this F. They're just a translation, a horizontal translation. The function in A is 1 unit moved to the left of the function in B. And the reason why this matters is because the derivative of a function, whether we are here, if this is A and if this is B, so they're both still ln functions, whether you're looking for the derivative at 0 here or the derivative at 1 here, notice how those two derivatives are still the same just because we're moving the function, right? So this fits with our sanity check. And what a good exercise to do is notice that C and D are also just translations, but not only horizontal, but also upwards, vertical translations. And see if you can do a quick little sanity check to see, convince yourself why the limits should be the same. Neat. Okay, let's keep going. Aha, so for what values of r does the function y equal to e to the power of rx satisfy this equation? What's kind of neat is, first off, this is called a differential equation. Differential equation. And a differential equation is just any equation where derivatives are used, and the things that you plug into the equation aren't numbers, they're functions, right? So here we're plugging in the function y into this differential equation. So there's going to be a future course, Math 2Z03, for anyone in engineering, or Math 2CO3 if you want to take this as an elective if you're in like science or if you're in computer science. And these two courses both focus on differential equations. So actually one thing I'd like to point out, this is not Calc 3. It's not Calc 3. Calc 3 is actually the one that's 2ZZ. It's called Math 4, but that's actually Calc 3. But anyways, so I digress. Let's just check to see if this function satisfies this differential equation here. So if we take one derivative, y prime is going to be r e to the rx from our chain rule, and similarly y double prime is equal to r squared e to the rx. So we want it to satisfy this differential equation, so we're going to plug in, we have r squared e to the rx plus 6r e to the rx minus 7 e to the rx equals 0. We can divide both sides by e to the rx because e to the rx is never 0. So we're left with r squared plus 6r minus 7 is equal to 0. So if we were to factor it, we could get r minus 1 and r plus 7 equals 0. And that gives us that r is equal to 1 and r is negative 7. Now also we need to check to see if any other values, because you notice we have actually no, I think that should be it. So 1 and negative 7. In particular, it's x if r is 0 would satisfy that equation as well. But if we were to plug in 0 for r, then we would get e to the 0, which is 1. And then since our chain rule would come down, we'd have 1 is equal to 0. So that's no good. All right, so let's keep going. Aha, find constants a and b, so the function y is equal to a sine of x plus b cos of x satisfies this differential equation. This is actually going to be closely related to another concept in Math 2ZA3 called the method of undetermined coefficients, which is used to solve differential equations. So we'll just try this one out really quick. So if we were to take a derivative here, y prime is equal to a cosine of x minus b sine of x, and then y double prime is equal to negative a sine of x minus b cosine of x. If we were to sum these together, so then we have y double prime plus 2y prime, so y double prime is a negative a sine x minus b cosine of x, plus 2 times y prime, a cosine of x minus b sine of x, minus y, so minus a sine of x, minus, I'm going to expand that in, b cosine of x. So if we were to simplify this here, we'd have the a sine of x's, so 2 of them here. And then we also, so this is going to give us negative 2a sine of x. Now we have also 2 negative b cosine of x's, so negative 2b cosine of x, plus we have 2a cosine of x minus 2b sine of x. So if we were to group this by our cosines and our sines here, so this is going to be equal to cosine of x, we have 2a minus 2b cosine of x, and then subtract 2a plus 2b sine of x. And we want this to be equal to cosine of x. So if this is equal to cosine of x, we need that this coefficient, we need 2a minus 2b to equal 1, and we need 2a plus 2b to equal 0. So if we were to solve this equation here, we're looking for the values for a and b, so we've got just a simple system here. So if we were to add these two equations together, we would get that 4a is equal to 1, and if we were to subtract these two equations, we would get 0 plus 4b, so that one subtract that one is equal to negative 1. So b is negative 1/4 and a is 1/4. Okay, cool, so that's not too bad. So let's take a look at question 20 here. This one says, consider the function f with graphs shown to the right. Which of the following statements are true? And it asks about 1, which says f is left continuous at x is equal to 1, 2, f is right continuous at x equal to 3, and 3, f is 1 to 1. And let's take a look. So here, first off, let's start with number 1. So if f is left continuous at x equal to 1, that would require that the left limit exist and also the function be defined. But you can see we have a hole at 1, so this one can't be true. Number 2 says the same, is f right continuous at x is equal to 3. Actually, since the hole is here on the right, we can't be right continuous at 3, although f is actually left continuous at 3 if we look at approaching from the left-hand side there. So now the only question is f 1 to 1? Remember that that would require f to pass the horizontal line test, but you can see f doesn't pass the horizontal line test here. If you were to maybe restrict the domain to a certain area, then maybe it could be 1 to 1, but as shown, f is not 1 to 1. Good stuff. All right. There are some more questions. I might finish those up after, but yeah. Thank you for